Hi, everyone. My name is Bridget Leonard, and I'm a recent psychology graduate from the University of Washington, Seattle. This is a pre-recorded presentation for CogSci 2023. The title of my presentation today is Faulty Memories, Favored Outcomes, How Errors Impact Learning Processes. Errors have previously been viewed as harmful to learning. In standard learning environments, we are often taught to avoid errors. This perspective stems from reinforcement paradigms, where errors represent an opportunity to reinforce incorrect behavior. However, for more declarative-based learning, such as memorization, errors do not seem to harm learning processes. For example, errors committed with higher confidence are actually more likely to be corrected. This suggests there is some process in which we are able to successfully learn from errors to aid memorization. A common way to investigate error learning or improvements in recall on subsequent fact presentations after an incorrect answer is the pretesting paradigm. During pretesting, participants generate an answer to a prompt before studying the correct answer. Since they have no prior exposure to the correct answer, participants are likely to generate an incorrect response. Although this paradigm encourages errors, pretesting leads to better recall on final tests than studying alone. While the pretesting paradigm commonly involves associated word pairs, research has extended its benefits to real-world materials like trivia and educational materials like math problems. Two theories of error learning are commonly referenced in pretesting literature. The elaborative hypothesis states that generating an error related to the cue and target helps form a richer network between them. In a word pair association task, one may generate the error tail in response to the cue whale when the correct word is swims. An individual could encode a meaningful story with the error, such as a whale using its tail to swim. At future cue presentations, this elaborative memory will be easier to retrieve due to its grounding in a semantic network. The mediator hypothesis suggests a more episodic account for error learning, in which the error itself is remembered and used as a secondary cue to retrieve the target. In our example, instead of just remembering the word swims in response to the cue whale, one could remember their error tail and use it to create an additional retrieval pathway to get to the target. Although these theories are well documented, investigation into the actual mechanisms behind them is sparse. We need a precise implementation of these two theories that reflects real human cognition, pointing us in the direction of Akhtar's declarative memory. Akhtar is a popular cognitive architecture that models information processing, memory retrieval, procedural execution, and human performance. Its declarative module encodes each memory in a semantic network. The activation of each memory depends on how recently and frequently you've seen it, or its base level activation, and how related it is to the current context, or spreading activation. Here we have the activation equation for a memory, or chunk I, that is the sum of the chunk's presentations and their decay based on when you encountered them, plus spreading activation from the current environment, plus some noise that models the noise of the human brain. Akhtar also includes a procedural module, which articulates cognitive steps that fire when the states of other modules meet their condition. To model the elaborative hypothesis within the Akhtar architecture, we use spreading activation. As we discussed in the activation equation, spreading activation reflects activation given to a chunk based on how related it is to the current context. After errors are made and corrective feedback is given, error information is encoded alongside the correct word pair chunk. We see that chunk 4 is more elaborative due to this extra information that's encoded in it. This extra information attracts more spreading activation than study chunks because it references the cue twice, and in this way is more related to the current context. The mediator method can be modeled by adding an additional production rule that detects errors when they have been retrieved from long-term memory. From the error, it can retrieve the correct target, allowing for a second retrieval pathway other than the typical cue to target pathway. Both these models predict higher test accuracy for error items compared to study items. In the case of elaboration, it is due to more spreading activation. You can see in the figure below that chunk 3 is a more elaborative chunk, referencing the cue twice, which is going to attract more spreading activation when subsequent presentations of the fact are given. In the case of mediation, error items will have better test accuracy than study items due to that additional retrieval pathway. As you see in the figure, instead of just using the typical whale to swims retrieval route, we also use an additional retrieval route that can go from whale to the air tail to the correct target swims. Although these models both predict higher test accuracy for error items compared to study items, they make opposite predictions for differences in response times. And this is based on the ACT-R architecture. In ACT-R, the retrieval time of an item, I, is based on the activation of I, such that higher activation leads to faster response times, depending on the individual parameter K, which accounts for individual differences in retrieval latencies. In elaboration, the activation of an error item E is increased from additional spreading activation, so that it is equal to the activation of a study item I plus the extra spreading activation S of E. We can incorporate this into the response time equation. Because the spreading activation of the error item will be greater than 0, the denominator of our equation will be greater than 1 and lead us to have faster response times for errors compared to study items. In mediation, individuals can retrieve an error, then remember it is incorrect and use it to retrieve the target. Since retrieval time is similar for correct, incorrect, and study items, on the fraction of trials F in which an error is retrieved, the overall response time will be double that of a study item response time. Because F is predicted to occur on at least some of the trials, we can expect the average response times for error items to be longer than study items. To support our models, we collected behavioral data using a pre-testing paradigm in which students memorized 60 different weakly related word pairs. In the learning phase, participants learned each word pair once in either an error or study trial. In the error condition, participants generated a response to the keyword that was most often incorrect, since word pairs are weakly related and hard to correctly guess. After studying, they were then given time to study the correct word pair. In the study condition, participants studied both the cue and target words on the screen. Altogether, error and study conditions both took 10 seconds to complete. After a distractor to prevent rehearsal, participants took a self-paced final test on all 60 word pairs. To analyze our accuracy results, we used mixed linear models to account for individual differences and variability. We fitted a mixed model to all experimental trials with condition, either error or study trial, as a fixed effect, and a participant level intercept as a random effect to account for individual differences in response accuracies. We also used a binomial distribution to capture the predicted variable, whether someone was correct or incorrect. As seen in the figure, we found a large and significant main effect of condition, such that on average, participants had better accuracy on error items than study items on the final test. The left column in our figure reflects the human behavioral data we collected, and the right column is our predicted model data, which you can see closely fits our collected averages. This data strongly supports that error learning does exist, showing that people did learn better when using an error trial to learn their word pairs compared to a study trial to learn the word pairs. Before running analysis on response times, we cleaned our data to only look at correct responses in a reasonable time range to remove various messy data like quick I don't know responses and long timeouts. We then fit a mixed model with the same fixed and random effect as our accuracy model. Condition error or study trial was the fixed effect, and we had a participant level intercept as a random effect to account for individual difference in response time latencies. We found a large and significant main effect of condition, such that, on average, participants spent longer responding to error items on the final test than study items. These response time findings support mediation, suggesting that this extra time responding to error items may reflect an additional retrieval pathway. A second mixed linear model was created with a participant level slope as a random effect. This allows individuals to have either a shorter or a longer response time in the error condition to examine if individuals are using different strategies, like elaboration. This model also found a significant main effect of condition, but did not provide a greater fit than the original model. Additionally, all the fitted slopes of the model were negative, suggesting that positive slopes in the original model are due to outlier responses and not systematic use of the elaborative model. Our analysis strongly supports error learning with strong evidence for mediation. Our mixed linear model for accuracy demonstrated that participants had better test accuracy on error items compared to study items, which supports past pretesting literature. Additionally, the difference in response times revealed in our mixed linear model supports a mediator method of error learning. Our more complex mixed linear model with a random slope for participants had all negative slopes, showing that no participants were using an elaborative model systematically. These findings suggest that errors can be used to further optimize learning paradigms. For example, by advocating for pre-study retrieval attempts and also recognizing that longer response times do not necessarily reflect weaker memories. To fully harness the power of errors in learning, we must, one, identify mechanisms, which we have begun to do through the use of computational models in this study. However, alternative explanations of longer response times must be examined in this framework to comprehensively understand error learning. Second, we must also understand individual differences, which can be looked at in the scope of computational models of different mechanisms, but might also exist more broadly in the fact that some individuals may not learn from errors at all. And finally, we must look at the effect of errors on alternative measures of memory. Accuracy is not the most reliable measure, and new research in learning and memory has established more stable and individual specific parameters, like the speed of forgetting, or how fast a person's memory traces typically decay. Thank you for listening to my presentation today. I would like to thank my advisor, Dr. Andrea Stocco, and my mentor, Holly Hake, as well as our lab, CCDL at UW. Thank you.